Today I'll be talking about some joint work with Edwin Tang, who presented our recipe paper a couple of days ago, Liling Gong, Avishai Livne, and Chelsea Brunetti. And what we're going to do in this work is figure out how we can make networks spill the beans. And the question we're asking is, what do the dynamic interactions tell us about information flow? And by dynamic interactions, I mean people are communicating, right? So instead of having a bunch of static links, we have links that are activated with information flowing over them. So the question is, if there's some big news, hey, they're selling these plush animals that are actually giant microbes, such as the common cold, does that look different from when there's really not much news? So for example, these two people are talking about their kids, and then some others are talking about weather or TV or politics or weather again, right? So simply by looking at the structure, can we tell what's going on? Now, there's been nice prior work on temporal networks. In fact, at the NetSci conference, there was an entire session just on temporal networks. And here's some earlier work. For example, we know that networks densify over time. We know that the community structure can change, and sometimes those changes signal some other process happening. For example, the Supreme Court shifting in ideology. Also, when you're studying the propagation of things like disease or information, it's really important to know when certain edges are there and when they're not, because otherwise the bug can't be transferred. And finally, there's some work examining specifically the Enron email corpus and looking at the structure when the participants are discussing something legit and when they're discussing something that's illegitimate. And when it's illegitimate, it tends to be much more dispersed. So what's different here? Well, we're going to, instead of just looking at community structure, we're going to look at lots of different network variables, and we're going to construct time series of them. And instead of just looking for single events, detecting them in the network, we're going to continuously try and infer what is the novelty and diversity of the information being shared. So just to recap, right, you can imagine that you're at a dinner party and you can't really hear what everyone is saying, right? There's kind of some chatter and you can tell who's talking with whom, but you can't hear what they're saying. And the question is, can you infer whether something new has happened? You know, perhaps someone saying, hey, I just got a new awesome paper published, right? And everyone's kind of reacting to that. Or perhaps it's just background chatter, there's really nothing of significance and everyone's talking about something different. So for our data sets, we use three. I'll describe two of them. The first one is the virtual world Second Life. And in Second Life, if you want to figure out where to go, you would use landmarks, which are coordinates within the virtual world, which you can share with others. They're like bookmarks, and once you have it, you can just teleport directly to that location. The other is that once you're at that location, you may want to be able to move your avatar around in a certain way. So for example, if you landed in a dance club and everyone has super groovy moves and you're just standing there stiff because you don't have a little script that makes your avatar move, well, one of the other users can give that script to you, and that's another asset that we track the flow of. And we study the top 100 most active groups in terms of asset transfers. The second context we study is Twitter. In Twitter, you of course have the follower-followee graph, but that one evolves very, very slowly. So instead, we're going to look at just the @replies and the retweets for kind of direct interactions between the users. The sample we chose was really one of convenience. Liling Gong, she found this list of researchers who are on Twitter. We then collected all of the accounts that those accounts followed, and she ran a community finding algorithm to find communities within those lists. We then took, all of the tweets, all of the asset transfers, and we segmented them. So for Twitter, we segmented by every 800 tweets, and the median segment duration was 1.5 days. In Second Life, we segmented by every 50 asset transfers, and that was a little bit over a week, typically on average. What you can tell from this figure is that these networks are actually highly dynamic. So already in the next segment for Second Life, you have about a quarter of the edges are preserved. The rest are not repeated segment to segment. And for Twitter, it's only about a fifth, right? So there's potentially a lot of information there because these networks really are changing. And what we're going to do is we're going to throw a whole bunch of network metrics at them. Centralization, what is the size of the largest connected component, what is the clustering, how much reciprocity is there, what is the average degree, et cetera, but we would also like to capture the potential for information to flow. And for this, we're going to use this conductance measure. The cycle-free effective conductance is the probability that if you start at A, you will reach B before cycling back on A. And the more paths there are from A to B, the higher the conductance. The shorter those paths are, so you're not going to wander off somewhere else, the higher the conductance. And if those paths don't go through hubs, because if you reach a hub, right, there are lots of other directions that you can wander in. Again, like not going through hubs will increase the conductance. And then what we did was we just summed the conductance over all connected pairs such that we had some sort of aggregate measure for that segment of how much potential information flow there is. We also wanted a measure that would capture how, colors are really awful, okay. How expected the network is. The simplest such measure would just be an edge to card, which is just the intersection over the union of the sets of edges in neighboring time segments. But this misses the fact that a lot of the ways in which networks evolve are things like triadic closure. So if A talks to B and B talks to C, then you would expect that maybe A starts talking to C. And this is exactly what our conductance measure actually captures. So if in the previous time segment there was high conductance between A and C, we're less surprised to see A and C start to talk. And so here, I'm not sure if you can see, but going from this network to this network, we have triadic closure, and most of the edges are the same, and so this is an expected configuration versus if it gets completely reshuffled, then it's unexpected. So we have this expectedness measure as well. So here's just a toy example. If you have a 3-node network with 2 edges, the conductance is 4. If the same thing repeats in the next segment, the conductance, of course, stays the same. The expectedness is high, it's 1.5, and the edge of card is 1. The edges are exactly the same. Now, if we close that triad, the conductance increases a little bit. The expectedness doesn't drop much at all because we had expected A and C to start talking, and the edge to card fails to capture this. It has dropped quite a bit. And then if we add another node, the conductance goes up, but the expectedness and edge to card go down. So if we start looking at these segments, so this is in Second Life, just two example segments. We have one that has low conductance and one that has somewhat higher conductance. In the low conductance one, there's one dominant landmark that's being traded that has to do with fashion. It's for a boutique. And actually, a bunch of the other dominant assets being traded are also landmarks having to do with fashion. In the high conductance segment, however, you have no landmark dominating and lots of diverse locations being traded. Now, when we do this overall, when we construct the time series, we have all of our network variables here, and then we have the overlap in the assets being traded and the diversity of those assets. And what you can see is that most of the network metrics actually don't correlate with properties of the information of what's being traded, but our conductance and expectedness measures do. So for example, when the conductance is high, you have high diversity in what's being traded. And when the network is as you would expect, then the overlap in the assets being traded is also higher. And although I should mention that in general, similarity and novelty are positively correlated, meaning that when there's something novel, it tends to capture more of the attention of the network. So here is the WikiLeaks story breaking in one of the Twitter communities. So the conductance increases from here to here as people are engaged in conversation about WikiLeaks. And then once it stops being so interesting, right, it falls again. And for Twitter, we're constructing the network a little bit differently because tweets are so short, it's a bit difficult to tell what people are talking about. So we don't want to only include the tweets that are interactions between the different accounts. We also want to just capture all the tweets. And this actually gives us lots of isolates because many of the tweets don't contain reference to other users. So when we calculate similarity, we're going to consider different kinds of pairs. So the first kind of pair is the one that's directly connected, right? So these two accounts mentioned each other in that time period. Ones that are in separate components, so you can't connect them during that time segment, and ones that are indirectly connected during that time segment. And for the similarity measure, we're just going to use cosine similarity of everything that the person tweets during that time period. For the novelty metric, what we do is we aggregate all the tweets by everyone in a given time segment. We construct the language model, and then we calculate the KL divergence between the language models in consecutive time segments. What we find for Twitter is that the correlations are higher. And we think this is because, first of all, many of the network metrics capture is there interaction at all, right? Because are people mentioning each other or not? And first, let me point out that for users who are directly connected, the correlations are low. What individuals who are mentioning each other are saying is very similar to each other, but it doesn't depend as much on what the rest of the network is doing. Two variables that do matter are, for example, conductance and reciprocity, both of which capture whether there's some back and forth between individuals. Then if we look at the indirectly connected nodes, what we find is that the denser and the more interaction there is, for example, if you look at the number of edges and the average degree and the conductance as well, the more similar those tweets are, which sort of makes sense. If you're part of the same conversation, even if it's not direct, you're more likely to be saying something similar. On the other hand, and here these two are very similar because most pairs are unconnected because these are fairly sparse graphs. What you see is sort of the opposite. That is, if you have high conductance, meaning that the rest of the network is kind of connected, and yet these two accounts find themselves in separate components, then they're less likely to be similar. Okay, so far we've shown that there is this correspondence between purely structural features of the communication network and properties of the information that's being traded. So can we actually plug this into a nice little regression and see if we can do predictions? If we can, go back to that dinner party and figure out, hey, was there something interesting I was missing out on when everyone was chatting? And so this is just what we'll do, and we'll also, since we have both the different kinds of similarities between different kinds of pairs, we can also put those in as semantic variables. So here, we're going to predict the similarity of nodes that are not connected at all. And we can use information about how similar the connected nodes are, how similar the indirectly connected nodes are, and then we have a bunch of structural features of the network. And the upshot of this is that even if we don't use the semantic features, how similar the other pairs of nodes are, we can predict very well what the similarity is between the disconnected pairs. We can also look at novelty, and here I'll just focus on the nodes that have at least one interaction, at least one neighbor in the graph. And here, as you might expect, if there's higher expectedness, there's lower KL divergence, meaning that the content also hasn't changed that much if it's the same people talking to each other. So we were a little bit concerned that we were getting different results depending on how we constructed the network and what the network was. So we devised a simulation where everyone is sending and receiving messages, and they're just a real number between 0 and 1. And your probability of sending out the message has to do with the recency of the message, but also how novel it is. And so, for example, if you've been getting a lot of 0.2s and 0.3s, if you see a 0.9, that's going to be very novel. You're going to be excited about it. You're going to send it out to more people and more quickly. Or maybe there's just some externally driven topicality. So 0.5 is really important this week, but 0.8 is going to be really central next week. And what we find is that when novelty is the primary driver, you get high correlation between network and in kind of the content variables. This is similar to the Twitter network, where you're looking at disconnected pairs. On the other hand, when it's the topicality that's driving exchange, then a lot of the correlations are reduced, and it starts to look like the connected pairs in Twitter and the Second Life interactions. So to conclude, we just showed this connection. I mean, you would expect it, but it's nice to quantify it. And what's more, you can actually predict one from the other, which is just that when we communicate, we're actually revealing something about what we're communicating about. But there are these caveats where it depends on how you construct the network, et cetera. So what we'd like to do in the future is figure out, how sensitive is it to the definition of the community? Who's in, who's out? Is it really right to chop up the communication into these segments, or should we actually be devising continuous measures of both network properties and content properties? What are the roles of the individual nodes? Is there actually more signal if you're seeing who's sending the messages in particular, as opposed to these kind of aggregate network metrics? Finally, I'd like to thank my co-authors on this and the funding source. Thanks.